Hi everyone, I hope you're all doing well and you had a nice weekend. You might have heard that spring break has been canceled, which is a huge bummer. The idea is that we want to make sure that everyone is staying safe inside. And so we want to make sure that everyone has lots of stuff to do over that week. You're not getting too bored. So we will be having school, but it's not going to be normal school. We're going to be focusing on some like fun enrichment activities. So you'll see that starting this week on Friday. And all of next week as well, we'll be focusing on some fun stuff that's mostly not going to be impacting your grade very much. Okay, other class announcements. You should have by now all taken the equilibrium and rates of reaction practice test. I'm gonna grade the short answer part and have that back to you pretty soon. So I'll let you know when I'm done grading that. All right, last week we very first introduced the idea of organic chemistry. Today we're gonna dive in a lot deeper and start talking about organic chemistry in a lot more depth. So let's get started. Okay, so I've pulled up a PowerPoint that actually has a do now for you to do. Of course, I'm not there to see you, but I promise you, you're gonna learn a lot more if you actually go through and do every single one of the example problems. So take a couple minutes right now to pull out your notes, pull out your reference table, pull out a pencil, actually do these questions, actually solve them out. Take a couple minutes to do that. Cool. Let's look at these Lewis dot structures. So CH3Cl, chlorine starts with 7 electrons. It needs 8 to be stable, right? Carbon starts with 4. It needs 4 more. It needs 8 total to be stable. Hydrogen starts with 1. It needs 2, only 2 to be stable because it's in that very first group. So the way to accomplish this is like this, where carbon is bonded to the 3 hydrogens and bonded to chlorine. Carbon's got 2, 4, 6, 8 electrons, so it's stable. Chlorine's got 2, 4, 6, 8 electrons, so it's stable as well. C2H4 is maybe a little bit trickier. If you try to do this all with single bonds, you're going to actually run out of electrons because there's only, carbon starts with 4, so 2 times 4 is 8, plus 4 more, so there's only 12 total electrons. And so you're going to run out of electrons if you try to make all single bonds. The only way to accomplish this Lewis dot structure and actually have the correct number of electrons and follow the octet rule is like this with a double bond. So each carbon starts with 4, right? So we started with 12 electrons and we've got 2, 4, 6, 8, 10, 12. So we have the right total number of electrons. And then just to check the octet rule, right, this carbon has 2, 4, 6, 8, so it's following the octet rule. Same with this one, 2, 4, 6, 8. So both carbons are following the octet rule. Okay, and then for number C, the correct way to draw this Lewis dot structure is like this, where carbon is making a double bond to oxygen. Oxygen, if you remember, starts with 6 electrons. So it's keeping 4 and it's putting 2 into these bonds, right? Carbon is also putting 2 into the bonds, right? So 1 into each bond. This is the best way to draw the Lewis dot structure for CH2O. Carbon's following the octet rule, 2, 4, 6, 8. Oxygen's following the octet rule, 2, 4, 6, 8. And we have the correct total number of electrons. Cool. And then just as a reminder, right, carbon usually makes, we can see from our Lewis dot structure, 4 bonds. Right here it's making 4 different bonds. Here it's making 1, 2, and then a double. Same here. But it basically always makes 4 bonds. Hydrogen only ever makes 1 bond because hydrogen is stable with 2 electrons. Any more electrons would be too many. It would be unstable again. So hydrogen always makes exactly 1 bond. So this is key information going forward because when we're talking about organic chemistry, we're going to be using a lot of carbon and hydrogen. So carbon always is making 4 bonds. Hydrogen is always making 1. Good. We talked a little bit about organic chemistry last time, right? Just to clarify, organic chemistry is the study of carbon-containing compounds. So we're gonna be looking at carbon a lot. It's a super interesting element because it makes 4 bonds. It can do that in a lot of different ways. It can make 4 single bonds, it can make some double bonds, it can make triple bonds. And so it's very diverse and it makes a lot of different compounds. But it's important to know, always makes 4 bonds. Cool. If you take a look at this molecule, you might not recognize the molecule from the picture here. This is a sort of organic chemistry shorthand where each of these little angles or bends is a carbon atom. And there's some invisible hydrogens that no one's bothered to draw in because we're too lazy. The technical name for this molecule is N-methyl-1-phenylpropan-2-amine, which, you know, try saying that out loud. But it's more commonly known, of course, as meth, because everyone's too lazy to say N-methyl-1-phenylpropan-2-amine. We're going to talk a lot about naming organic molecules, and we're going to start to see where some of the parts of this name come from. For today, we're going to focus on simpler molecules. We're going to start with hydrocarbons. A hydrocarbon is basically what it sounds like. It's a molecule that just has hydrogen and carbon. Right? So this is not a hydrocarbon because it's also got nitrogen. Hydrocarbons are our simplest organic molecules. It's compounds containing only hydrogen and carbon. Let's take a look at some hydrocarbons. So here is a set of 3 different lists of hydrocarbons. Take 2 minutes, I'm gonna time you, take 2 minutes and draw as many of these as you can. And I would go row by row rather than column by column, just to make sure that you get a few from each of the 3 different groups. Take a couple minutes to do that. Okay, on your mark, get set, go. You get 2 minutes. One more minute. All right, let's take a look at these. So the first group, and then we want to think about like what do we notice about these 3 different groups. So let's look at each one individually. Let's look at this first group, this first column over here. So if we look at the first column, the first list out structure is going to look something like this, right? We've got 2 carbons, and then each carbon is bonded to the other carbon, and then to 3 hydrogens, so 6 hydrogens total. On the next one, we've got 3 carbons and 8 hydrogens, so 3 on the end, 2 in the middle, 3 on the end. Next one, C5H12. So we've got 5 carbons. There's 3 hydrogens on the end, then 2 hydrogens, 2 hydrogens, 2, 2, and then 3 on the other end. Okay, C7H16, that's gonna look like this. We've got all 7 carbons, right? 3 hydrogens on the end, 2, 2, 2, 2, 2, 3 on the far end. Okay, and then last one, C8, H18, that's not right, this has 6. Well, whatever. We don't have the Lissat structure for this one, but it would look pretty much like this one, except instead of 7 carbons, there'd be an extra carbon squashed in here with 2 more hydrogens right above and below, because we've got 1 more carbon and 2 more hydrogens. So 1 extra carbon with a hydrogen above and a hydrogen below. Cool. Let's look at the next group. Okay, so C2H4, that was for our do now, that's this one. C3H6 is gonna look something like this. You might have the double bond on the other side, that's fine. We're going to have a carbon that's making a double bond with 2 hydrogens. Then this carbon has 1 hydrogen, right? And it's, remember, carbon only makes 4 bonds. This one has 1, 2, 3, 4. So it's stable with just being bonded to the 1 hydrogen. And then the carbon on the end that's bonded to this carbon and 3 hydrogens. C5H10 is gonna look something like this. You might have drawn the double bond somewhere in the middle, right? That's also fine. C7H14 is gonna look something like this. This is actually C6H12, but C7H14, we just have an extra carbon and 2 hydrogens, right? And C8H16 I didn't include because it didn't fit on this PowerPoint slide. So you might notice already something that everything in this group has in common, but let's look at the third group. So C2H2, right? Here's C2H4. If we get rid of 2 of these hydrogens, right, in order for carbon to make 4 bonds, well, it's making 1 bond to a hydrogen, it's got to be making 3 bonds to the other carbon. And so the structure is going to look like this. That's the only way for carbon to make 4 bonds, which is the only way for it to follow the octet rule and be stable. C3H4, there's a couple of different ways to draw this, but the most common way is like this, right, where you've got the 3 carbons. These 2 carbons have a triple bond. This carbon has a single bond to this other carbon. This carbon's not bonded to any hydrogens because it's got 3 bonds to this carbon and 1 to the other carbon, right? This carbon's got 3 hydrogens. This carbon's got 1 hydrogen. C5H8, a couple of different ways to draw this, but here's one of them, right? 1, 2, 3, 4, 5. And we've got this nice triple bond, and we've got our 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And remember, every carbon has 4 bonds. Every hydrogen has 1 bond. Cool. So let's think about what we notice about these 3 groups, right? Hopefully you've noticed something about the first group, something about the second group, and something about the third group. We can now take a minute to write a mathematical formula for each of these groups. So a mathematical formula would be something like CNH, something with N in it, right? So if we look at the first group, right, in the first group, we always had, here we go, we always had the carbons on the end, which always had 3 hydrogens, and then all of the other carbons in the middle always had 2 hydrogens. So it's kind of like, well, every carbon has 2 hydrogens, but then there's also always these 2 extra hydrogens on the end to make sure that the carbons on the end have 4 bonds. So we could write a formula that looks something like CNH2N plus 2 to show that however many carbons there are, there's always twice that many hydrogens and then plus 2 extras on the end. And if we look at this list, everything in this list follows that, right? So C2H, then this would be 2 times 2, which is 4, plus 2, which is 6. So C2H6. C3, that means N is 3 for the second one. H would be 2 times 3 plus 2, so that's 6 plus 2, that's 8. So C3H8. For the last one, right, CN, N is 8 for this last one. H would be 2 times 8, so that's 16 plus 2 is 18. So C8H18. Take a minute and see if you can write a formula for the other 2 lists. For the middle list, we can write our formula as CNH2N. For the last list, we've got exactly 2 fewer hydrogens for all of these. So this would be CNH2N minus 2, right? So if we look, for example, at the last one, when N is 8, H would be 2 times 8, that's 16, minus 2 is 14. Good. If you we can actually find these formulas in our reference table. So go ahead and pull out your reference table. If you don't have it, Google chemistry reference table. It'll be the first hit. Open that up. Go to table Q. Each of these groups has a name, right? And they also all have a special, thing they all have in common, right? So with our first group, if you're looking at table Q, you'll see that the first group is called alkanes. The second group is called alkenes, and the third group is called alkynes. The alkanes all contain all single bonds. It's all carbons with all single bonds, right? The alkenes have a double bond, and the alkynes each have a triple bond. So those are our three big groups of hydrocarbons: alkanes with all single bonds, alkenes which have one double bond, right? It's not all double bonds, it's one double bond, and alkynes which have one triple bond. Take a minute to classify each of these compounds as either an alkane, an alkene, or an alkyne, right? If you wanted to, you could draw the Lewis-Staff structure, but that's kind of long and tedious. It's easier to match it to this formula, right? Look at the chemical formula and see which of these general formulas it matches. So C10H8, let's see, 10 times 2 would be 20, and we've got 18 hydrogens, so this is like 2N minus 2. So that's this group, right? So that's an alkyne. Take a minute and work through the rest of these. All right, so C3H6, that's an alkene. C4H10, alkane. C7H16, alkane again. Alkene, alkyne, alkane. Good. We're gonna use these rules to help us name all of these compounds. So right now we've just been classifying it into which of these major groups it falls into. Now we want to name each individual molecule, right? Every formula is going to have a different name. The way we name simple hydrocarbons is with two parts. There's a prefix and a suffix, right? So C3H8 is propane, C3H6 is propene, C3H4 is propyne. So let's think about what's determining the suffix. You might have noticed that there's a different number of hydrogens for each of these compounds, right? The different number of hydrogens is what gives us the suffix, right? All of these have the same number of carbons, and they all have the same prefix. So the suffix is based on whether something's an alkene, alkene, or alkyne, right? Something that's an alkane gets the suffix ane. Something that's an alkene gets the suffix ene. Something that's an alkyne gets the suffix yne. If we look at the prefix, right, here are three different molecules that have different prefixes, right? Propane, butane, pentane. So let's think about what's determining the prefix. The prefix here is based on the number of carbons. So the prefix basically is telling you how many carbons you have, and then the suffix is telling you what type of molecule it is, which lets you figure out how many hydrogens it's going to have. So in order to figure out the prefix, you have to know how many carbons are present and then use table P. Right? So if you look up in table P, 3 carbons gets the prefix prop. 4 carbons gets the prefix but. 5 gets the prefix pent, which is probably the one you're most familiar with because that's like pentagram. And then to find the suffix, you have to know which of those 3 groups, alkane, alkene, or alkyne it is. You can use table Q to help you figure that out. So let's look at an example, C5H10. Based on the number of carbons, right, I look up in table P, okay, what's the prefix if I have 5 carbons? That's pent. Then I have to figure out, is this an alkane, an alkene, or an alkyne? Well, I have 5 carbons, and then if you double 5, that's 10. 2N would be 10, and I've got 10 hydrogens. So I have twice as many hydrogens as carbons. So that's an alkene. So that would have the ending ene. So this is going to be pentene, not to be confused with the shampoo. So good, this is pentene. Take a minute to see if you can name each of these hydrocarbons. Cool. Okay, so we've got ethene, heptine, hexene, pentane, pentyne, propene, nonane. Make sure you check through your answers. If you've gotten any of them wrong and you're not sure why, let me know. Shoot me an email or come to office hours so we can go over it. Cool. Okay, what if we have the name and we want to know the formula, the chemical formula? So for example, what if I want to know the chemical formula for octane, which is mostly what gasoline is made of? Gasoline's not a pure substance. It's kind of a mixture of a bunch of stuff, but it's mostly octane. Well, the prefix tells us how many carbons there are, right? So oct, that prefix is telling us how many carbons. You can look it up in the reference table. You might even be able to guess without looking it up, right? Oct is the prefix for 8. So we've got 8 carbons. The suffix ane tells us we have an alkane. So that's the formula. The hydrogen is like 2n plus 2. So we've got C8, and then the hydrogen is going to be 2 times that, which is 16 plus 2. So CaH18. So we have an alkane with 8 carbons, right? Following this formula, C8H, H 2 times 8 plus 2, 18. Take a minute and see if you can write the formula for each of these. All right, here's the answers. There we go. So decene, C10, and then ENE tells us it's just double the hydrogens. So C10H20, propyne, right? Prop is C3, and then YNE tells us it's 2n minus 2. So that's like 2 times 3 is 6, minus 2 is 4, right? Hexane, C6H2n plus 2, so 2n would be 12, plus 2 is 14, C6H14, right? And so on. Again, let me know if you have questions. All right, I hope that was helpful and you all have a good idea about how to name organic hydrocarbons. Next time, we're going to start looking at more complex organic molecules, and we're going to build on after spring break. I will talk to you later. Bye.